So now I can start, right?
Right.
Okay.
Yes, please. Do so.
Thank you very much for the invitation to this nice conference. And today, I'd like to present you results of the following two papers. The first paper is our joint work with Alexander Grigor'yan, Yuri Kondratiev, and Andrei Piatnitski, where we consider large time behavior of the fundamental solution of the non-local convolution type parabolic equation with regular time derivative. There is equation, parabolic equation of the following form. And the second paper, it is also our joint work with Yuri Kondratiev and Andrei Piatnitski. This work is a natural continuation of the first work, where we consider the fractional time derivative, and again the non-local convolution type operator in the right-hand side of the equation. So let us.
Excuse me, your slides are not moving.
Sorry.
Yeah, we still see the first one.
Oh, you see only first one. Oh, sorry. Just a second. Maybe I try again. Now, do you see the second slide?
Yeah, yes, now it changed.
Okay. So then I can start again. Sorry, I'm very sorry. I present to you results of the following two papers. The first paper is our joint work with Alexander Grigor'yan, Yuri Kondratiev, and Andrei Piatnitski. We consider this parabolic equation, parabolic type equation, where in the right-hand side you can see the non-local operator of the convolution type. And the second work is a continuation, natural continuation of the first work, when we consider, instead of the regular time derivative, the fractional time derivative. So is it okay? Now you see the next slide, right?
Yes.
Okay, so it works. I'm happy. So let us look on the parabolic equation in more details. In fact, this parabolic type equation, one can consider this like some approximation of the classical heat equation. Why? Because here, instead of the Laplacian, which is a generator of the diffusion process, we consider the generator, again, the generator, but continuous time jump Markov process with jump intensity equal to 1 and with jump distribution given by the kernel by the function A. So if we assume this normalization for our function, then we can write this operator, this generator in the following short way. And if we consider the solution of the equation, then the solution defines the distribution of this Markov process at time t, on the condition that the process starts at the origin. And this connection with the probability theory is very important for us, because in some special region, when we consider the behavior of the fundamental solution, we really relied on the probabilistic arguments. And I'd like to say that this problem was formulated by Yuri Kondratiev, because this problem, it has very strong relation with the asymptotic analysis of so-called contact model in continuum in the critical regime. The contact model is a special type of the birth and death stochastic dynamics on the infinite particle configuration space. And this equation describes the evolution of the first correlation function of this model. And in fact, the first correlation function is a density of population. And of course, to have information about how the density evolves in time, it is very important for us. So we started to look on this problem more carefully, and now I formulate our results. So first I listed the assumption on the kernel. Okay, so A, because it is a intensity of the jump. Of course, it is non-negative. Then we assume that A is bounded and it is integrable. Sorry. Then we assume, of course, symmetry, because we'd like to have some approximation to the diffusion type of operator. We assume normalization and also the existence of the second moment. In fact, these three conditions are quite natural, and additionally, we assume that our kernel has a so-called light tail, so it decays at least exponentially. Here, P is greater or equal to 1, and we also consider the case when the kernel has a bounded support. So in my talk, I tell you about the asymptotic. Asymptotic means that we consider large T, but different region and X. So we look on the asymptotic behavior of the fundamental solution of this equation, and I'd like to compare this fundamental solution with the classical heatkernel, so the solution of this parabolic equation. Yeah, here I show some drawing to explain what is real difference between these two operators. So if we look on this operator and look on this operator and the Fourier transform, that both of this operator are multiplications, operator of multiplication of the function. And in the first case, we have bounded function. Maybe it is not monotone, it can looks like this one, but it is bounded function. And the second function, of course, unbounded, but what is important that near the zero, in the boundary of the zero, the behavior of both of these functions are the same. They behave like a quadratic function. And we look how this different behavior will give us the information about the behavior of the fundamental solution of our equation. So fundamental solution in our case, since A is the bounded operator, can be written in the form of exponent. So we can consider exponent. A is convolution minus identity operator, and then we use the decomposition for the exponent with convolution in the following form. So we see that the fundamental solution of our problem is a sum of a singular part. So we have delta function with factor exponent minus t, and a regular part which has the following form. And in what follows, we consider, of course, the pointwise upper and lower bounds for the regular part of the function p. Now I very shortly to remind existing results about behavior of the fundamental solution or heatkernel. Of course, there is a huge literature, and I just mentioned some of them, which has some relation with my topic. So first of all, of course, heatkernel, and it is explicit expression for any t. Then I'd like to mention the general, very nice formula, very nice Aronson estimates for uniformly elliptic second order operator in divergence form, general parabolic equation, and there is a result about behavior of the fundamental solution for the fractional Laplacian operator. And very interesting result by Davis. He studied the lifetime behavior of the heatkernel of the discrete Laplace operator on a countable locally finite connected graph. And under the assumption that this graph has uniformly bounded degree, he obtained the following upper estimate. So this estimate has a form of large deviation result. And what is interesting here, that the rate function here behaves like a quadratic function near the zero, and like a function r logarithm r when r is large. And we will see later, then we obtain the similar result when, in the case when we consider our kernel function a as a function with a bounded support. We discuss this just in a few minutes. And now I prepare for formulating our result, and we consider different region in xt space. So I like to remind that t is large and x arbitrary. So we consider 4 different regions when we have different asymptotic formulas. So the first is standard or normal deviation region, then moderate deviation region, large deviation region, and extra large deviation region. Then x, of course, depends on the degree of parameter t out. So, for the first standard deviation region, we have, of course, it is well-known formula, and there is something new. It is just the following asymptotics. We have Gaussian law, and here, of course, we can use the approach which is based on the application of Fourier transform, and it is not surprised that we have the same asymptotic formula as for the classical heatkernel here. In the region of moderate deviation, it is still the same formula, but logarithmically. You see now there's the rest in the degree of exponent. And the most interesting case is the large deviation region. It is a new result, of course, and here we should introduce some special functions. So we introduce cumulant generating function and its Legendre transform. So a function E, which depends on R. R is a vector in RD. And this function, of course, defines in terms of our kernel A. And after that, we introduce a number xi. So R now like a parameter, R is parameter, and we consider the solution of this equation. And we prove the following lemma that under our condition on the kernel, there exists the unique solution of this equation for any R, which is non-zero, and this solution is just a real number between 0 and 1. And after that, we can introduce the rate function as follows. What is important for us that we have this explicit expression in terms of the Legendre transform of the cumulant function, and we can extract a lot of information about the behavior of the function, and we can prove the following. Yeah, and we prove the following result, which is in fact formulated as a result of large deviation. So if x behave like RT, R is a vector in RD, so x has the same order as t, then the regular part of the heat kernel has the following form for large t. And here the rate function exactly has the following representation. And what we can say about the behavior of the function phi. First of all, 0, it is 0, it is non-negative, it is a convex function, and it behaves for any a, it behaves like a quadratic function when I is small. And when I goes to infinity, it also goes to infinity. What we can say more, we can say that if we consider a with a finite support, that this function, it means the following bound from below. So it behaves, okay, it is estimate, but in some sense it is more or less sharp estimate. So it behaves not like a quadratic function, but as function R logarithm R. And it is in accordance with the result of Davis. And moreover, if we consider the kernel that satisfies the following two-sided bounds, with P, and P now the parameter of the decay of this kernel, then we obtain the following, that phi the function phi is linear, has the behavior like the first degree of R for large R, and behaves like to this one when P is greater than 1. So in both cases, you see that we don't have R square here, but not quadratic form for the function phi, but it is linear or linear and times some power of logarithm. And in extra large deviation region, we obtain the following bound. So there is bound from below, from above, I'm sorry. It is the bound in the case when P greater than or equal to 1. And if A has a finite support, then it is the following bound. Moreover, we can prove that again, if A satisfies two-sided estimate, so if A behaves like the exponent, that we can prove the two-sided also bound for the fundamental solution. And you see that it is exactly the same as in the made by Davis. And now I'd like to make some conclusions about the comparison of our result and the behavior of the classical heatkernel. So we'll see that in the we saw that in the region of normal and moderate deviation, the behavior is coincide. In the region of moderate deviation, it coincides with the logarithmic scale, and in the large deviation area, we start to see the divergence of in the behavior of these two functions. So when R is small, it is still similar, but when R is large, then for large R, the function phi behaves not like a quadratic function. And now on this slide, I try to draw the graphs of these two functions. Then maybe it is more evident the behavior and the difference, the divergence in the behavior of these two functions. So the blue line is the classical heatkernel, and the red one is the fundamental solution for heatkernel for our non-local problem. So you see that in the region of standard deviation and moderate deviation, they are mostly the same. And the difference, the divergence start in the region of large deviation region. Here it is still minus R squared t. And here we have the other function, other rate function phi r when I tends to infinity. And in the region of extra large deviation region, you see the crucial difference in the behavior of the classical heatkernel and our situation. Okay, so there is conclusion we compare with Davis, and now I think that I have maybe 5 or 7 minutes.
We also need 5 minutes for discussion.
Maybe shortly. I just maybe 3 minutes.
Shortly, please.
Yeah, shortly. I'm sorry. Just to look what's happened if we change and look not the and consider fractional time derivative. What is a change? In this case, we assume that A is again symmetric negative, and we assume that A is a continuous function with the same normalization and has very light A, so we assume that P is greater than 1. And to find the asymptotic for the fundamental solution in A, we use a very nice formula by Chen Kim Magai Wang, which is which give us this following. In terms of the density of the inverse alpha stable, and here the function is before. So in fact, we can use the information from our and consider the asymptotics of integral. Just a few, 1 minute more, because it is very elegant formula for the heat kernel in this case. So instead of exponent, we have now the Mittag-Leffler function, and instead of the this regular part which has the exponent, we again has this representation in terms of the derivatives of the Mittag-Leffler function, and we couldn't use. There is very nice formula, but we could not use it because we have no information about case derivatives of the Mittag-Leffler function, and we use again the previous formula after some rearrangement and change of the variables. In fact, we reduce this formula to the following one, where is so-called right function, and we use the asymptotic behavior of this right function due to the analysis by Grigor'yan flow with Mainardi, and eventually we have results. And in this case, we have more regions. And what is important for us, so there is some estimates. What is important then, the normal deviation, the region of the normal deviation has the order alpha divided on 2, 1/2 of alpha, and we have the explicit formula to the integral, and the large deviation region is the same as before. So we can expect that it is t in degree alpha, but no, it is the same region for large deviation, and of course with different rate function, and extra large deviation is the same. And there is expression for the rate function in this case, and that is all. Thank you for your attention.
Very much.
I'm in time.
Can you hear me? Thank you very much for your nice presentation. So let's thank you, our speaker. So as before, I first would like to ask the audience here in the room whether there are any questions. Is there anybody in? Now I'm asking the participants, the virtual participants, whether there are questions there. Okay. Well, let me ask the following question, which was also relevant in the previous talk, and this is degeneracy of your operator. What are the problems you experience, or one would experience if one would allow for degeneracies?
Maybe I do not understand your question. You mean about applications?
No, I was more interested in the in the techniques where you are using.
Technique.
Because I mean, you had the estimates for your
yes.
A, right? So you had bounds, up and lower bounds, and in particular also of the exponential type. But anyway, so
yeah,
but maybe we don't need to take up the question because we are a little bit in a hurry anyway. So, but you're welcome to answer.
Yeah, the technique, I already told that we use some probabilistic technique. It depends on the region, and we use estimate on the case convolution kernel. We use this representation, and we use very detailed information about case convolution kernel, and then we look what is a term, the main term in this decomposition, and estimate it more carefully.
Yes, thank you very much.
Thank you.
If there are no more questions, maybe somebody else will, since we are late, then let us thank the speaker again. So I would now like to ask Dr. Xiaozhuang Yang from Brunel University here in the room. And he will speak about multifractional analysis of path regularity of Levy type processes. Please, Dr.